Good evening, students. Welcome you back for another important lecture on solid state. We have already told you the different types of the unit cells. Students, we have told you primitive unit cells, simple cubic cells, body-centered, face-centered cubic unit cell students, and we have calculated the number of atoms per unit cell in each of them. Okay? We have
Yes, sir.
calculated how many atoms are there per unit cell in FCC. Students, how many atoms are there per unit cell in FCC?
In FCC, there are 1 plus 4.
In FCC, there are 4 unit cells. Okay. And how many atoms per unit cell in BCC, body-centered cubic lattice students?
In BCC, it is 1 plus 1, 2.
2. And in simple cubic?
In simple cubic, 1.
Okay, and today our lecture is going to be based on the closed pack structure, students. That what happens, we are saying, you already know that in solids, student, in solids, the constituent particles are very closely packed. The constituent particles, they are very closely packed. Okay? As
Yes,
close
sir.
as possible. And that is why the solids are very rigid, because the distance is between the particles is very small. They are having very strong attractive forces between them. But whenever packing will take place, student, there will be some space which will be left vacant.
Okay.
And the solids packing takes place in such a way so that there is a minimum student vacant space left between them. So that is what makes them more stable. Otherwise, if there is a lot of space between them, then they will not be stable, student. That is a point. So the constituent particles can be considered as hard spheres. They are
Okay.
hard,
Hard spheres.
hard spheres, student. So what will happen? The question now is that how will we arrange these particles and build up the structures of the crystal, students? So we will like to see that what type of closed packings are possible. How do we do closed packing, students? What we want is, student, closed packed structures. Closed packed structures. Okay? So that the minimum space is left between, minimum vacant space is left between the particles. It is just
Okay.
like that in a suitcase you are trying to pack certain cloth, students. The question is, you want more and more your clothes to get inside the suitcase, but you will see that certain space will be left vacant when you pack everything, and then you may put smaller things into those gaps. And what we are trying, students, hard spheres, constituent particles are, we are saying, hard sphere, so they will pack, but one cannot penetrate into another. It's very important that one sphere, one particle cannot go into the another particle. It can maximum touch the other particle, that's all.
Yes, sir. Yes, sir.
And there could be certain vacant spaces left. The first thing is, let us see in one dimension. In one dimension, student, when I say one dimension, I am talking of close packing in one dimension. In one dimension, what I will mean, there is only one way of arranging these particles in one way. So what will be that? You arrange them in a row, student, in a row. There is a row. What is a row, student? That here you see, this is my one particle. They are all of the same size. Okay? Here we
Yes,
are
sir.
saying they are of the same size. So they are hard sphere, student, like this, like this. This is a row. This is a row, student. As you can see, they are touching each other.
Yes, sir.
As here we have shown, student, these are the sphere, student. These are the constituent particle. As you can see, they are touching each other. If I consider this particle, student, it is surrounded by how many particles? How many particles are touching this?
2.
So therefore, the number of nearest neighbors, the number of nearest neighbors, student. The number of nearest neighbors is how much? How many particles?
Two. Two.
So it has a nearest neighbor. If you can see any one of them, this is the nearest neighbor one. This is the nearest neighbor two. Only two. So student, the coordination number is two. In close packing, coordination number will be two
Two.
in one dimensional, in one dimensional closed packing. In one dimensional closed packing, what will be the coordination number, student?
Two.
Here you can see what you are seeing, they are touching each other. They are touching each other. But students, if some other atom comes in between, what will happen? If there is another atom, what can happen? You see that these are the two particles. If some other atom comes in between, student, then what can happen? This is a what we call as a guest. This is the host, student.
Okay.
Host. The larger size is the host and this is a guest. There is a radius limitation of this. What radius can be there when it comes? Because if the radius of this will become too large, then this type of packing cannot sustain you, student, this particle. So we will study that later on, the radius ratios. This is there is a radius of the smaller one, and the larger one R. So you can see in books, this we don't want to go at this point, the radius ratios. The radius of the smaller ion divided by the radius of the bigger. That is something R by R, student. R is the radius of the guest and big R is the radius of the host. This is my host and this is the guest, student, which is coming in. So there is a limiting value of the radius ratio. You will see R by R. There is a limiting value of the radius ratio, student, which we will study later on separately, that what happens. There are always smaller particles which are in between the bigger particles, the vacant space.
Okay.
But how much it can sustain is only one dimensional. It is only one dimensional. For example, if you will consider the case of beryllium chloride, student, you know what is beryllium chloride? This molecule is linear. These are negative, student. These are larger anions, -1, and beryllium is 2 plus, smaller. See that it may be in between. So these two chloride ions, if I consider it to be one dimensional closed packing, certain information we will give you later on, just to tell you that what is happening, because the
Okay.
smaller cations are likely to be packed in the spaces which will be left, smaller particles. Bigger particles cannot come into the space which is very small. So the size of the particle is important and the radius ratios are important. What is the limit of the radius ratios? Just to tell you. So students, here what is the coordination number of, in this case, this beryllium is surrounded by how many? 2. So the coordination number is 2. The nearest neighbor that touch is 2, students. That is what we call as coordination number. So there is nothing much here, simple, only one row. Okay? You have arranged.
Yes, sir.
Okay. All right. Now, student, let us see close packing in 2 dimensions. In 2 dimensions, students, close packing in 2 dimension can be generated by the rows of close packed spheres, and there are 2 different ways. देखो, 1 to 2 dimensions I want to go. ठीक है?
Yes, sir.
So I have to put the second layer, student. Second layer of the atoms, and like this there will be layers of the atom, students.
Okay.
2 dimension. Now I am talking of 2 dimension. Then supposing, students, you put the first layer. You see, this is my first layer, students. As we have shown you, closed packing, closed packed first layer. Now, if you put another layer exactly below this, okay, I call this
Okay.
student A layer. This is
Okay.
my A layer student. What I say, this is A layer. And I put, they are same size as you can see. And I put another one exactly below this. Same type of layer, student. I repeat the layer without disturbing anything, student. What will happen? I am putting the same layer, student. No disturbance, no disturbance. Okay?
Okay.
This layer is A, student. This is A like this. I can put the layer, student. Okay? Now,
Yes, sir.
important point here is, what is the important point? Let us take another color, student. Important point is that, student, supposing I consider my this sphere. You can take anyone, no problem. If I take this student, how many constituent particles are touching this sphere? How many are touching this?
Four.
These, as you can see, student, these spheres of two rows are aligned horizontally as well as vertically. The what we are saying, student, the rows are aligned horizontally. What is horizontal? This is horizontal. And vertically. Okay?
Yes, sir.
So, student, you see that this atom is being touched by 1, 2, 3, and 4. So, here you can see that in this case, exactly what is happening, as you have shown here also, student, this one is the particle 1, 2, 3, 4. Only four nearest neighbors. How many here? This is touching, this is touching, this is touching. How many nearest neighbor, student?
Four.
Nearest neighbor. Coordination number. What is the coordination number, student, here? 4.
Four.
And if I will join the center of these, join the center of this, what shape it is coming, student?
Square.
Square. So, student, if you join, as we have seen here, student, this is a layer A. It is aligned with another layer A, both horizontally and vertically. Both horizontally and vertically. This is my vertical. This is my horizontal alignment. And we find that here, student, each sphere is in touch with four spheres. Coordination number is 4. The nearest neighbors are 4, students. And if I join the center of these nearest neighbors, then you will see a square. That is why this type of packing is called square closed packing. In two dimensions, student, I am saying in two dimensions, students, what you are getting. First, if I repeat the layers horizontally and vertically, they are aligned. A type arrangement, student. Okay? This is called
Yes, sir.
square close packing.
Square close packing.
Okay. Now, student, what we do, students, what we will do now, the first layer, supposing, student, this is my first layer, which I call as a layer, students. Okay? This is my A layer, students. Okay?
Yes, sir.
Now, what I do, student, I displace this. I displace this. What I displace the second layer. Second layer is displaced. Instead of putting the next atom aligned with this student, then you can see there is some depression here. ठीक है?
Yes, sir.
The second,
Yes, sir.
what will happen, student? The second row may be placed above the first one in staggered manner. In staggered manner, such
Okay.
that the spheres in that its spheres fit in the depressions of the first row. This is my first one. What I will do, the second layer, students, second layer. Wait a minute. What happened? This pen. Okay. So, student, what we are doing? The second layer. Second layer, student. First one is my A layer. Second layer, B layer. ठीक है? This I will
Yes, sir.
placed in a staggered manner such that its spheres fit in depressions of the first row. Its spheres fit in depressions of the A layer. ठीक है?
Okay.
Where are the depression? This is the depression. You can see this is the depression. ठीक है? This is the depression. This is the depression.
Yes, sir.
Depression.
Okay.
So my drawing may not be that good, student, so you can see. So the second layer is displaced. And then again you have the third layer, which is the same as the first layer.
Okay.
Yeah. So the next layer is again the same, student. So that layer will again be, if this is the point, student, it is coming exactly below this point. Okay?
Yes, sir.
So this is the point, student. Same. Now you can see what has happened, students. If I consider one of these, what will happen, students, now? See how many are going to touch with this student. A better drawing is shown here.
6.
Supposing this is the first layer, the second one you can see is displaced, staggered. These are the depression. ठीक है? In the depression, you are putting
Yes,
the
sir.
second layer. So you take any one student, sphere, anyone. How many it is touching?
6.
You can see how many it is touching, student. What is the nearest neighbor, student, here? What is the nearest neighbor in this case? So if I have student AB type arrangement in the two dimensions, students, what is happening? You are what type of shape? You can see the coordination number is 6 now, students. Coordination number
6.
6. So there are 6 nearest neighbors in such cases, students. And you can see when I take one of the sphere, it is touching with 6. If I join the center of the 6 nearest neighbor, it will look like, student, hexagonal shape. What shape it has? The shape
Hexagonal.
is regular hexagon. What is the shape of that? Regular hexagon.
Hexagonal.
Therefore, this type of packing is called, student, two-dimensional hexagonal closed packing. So in 2 dimensions, we are having 2 types of packing. Okay? In
Yes,
2
sir.
dimensions, I am saying in 2 dimensions, student, I have 2 types. One is a square. One is square closed backing,
That one. Other is hexagonal.
hexagonal closed backing. This is two dimensions. Now the question is, out of these two student, there are empty spaces which you can see in this. ठीक है? These are
Yes, sir.
this you can see empty spaces. You can see empty spaces here also. This is the empty space here. You can see that this is the empty space, student, in square close packing, and in this you can see these are the empty spaces, student. Empty spaces you can see, and the you can see this empty spaces, and what is the other one? Here you see empty spaces visible, which is a better packing,
Yes, sir.
which is more close packing in this case, which is more efficient packing, which is more packed, student, hexagonal, or
Hexagonal.
in this there is a less
Hexagonal.
vacant space, student. This is less efficient. This has a more vacant space. There is a more vacant space in this, and this is a more efficient, more closer packing as compared to hexagonal. Close packing is more efficient. There is a less vacant space in this. There is a less vacant space in this. ठीक है? In this is
Yes, sir.
more efficient, which we will see later on what is the meaning of that. More efficient closed packing in two dimension. In two dimensions. As compared to this, there is a more vacant space left here, more vacant space in this as compared to hexagonal closed packing, HCP. So there are some voids, empty spaces are called voids, student. What are voids? Empty
The
space.
empty spaces.
Because they are important. And you see what will happen, those particles, those constituent particles which are smaller in size, they can fit into it depending on the radius ratios, which we will tell you what are the limiting values of the radius ratio. The smaller ones will go inside this. That depends on the size of the void which is created, because there are different type of voids: tetrahedral, octahedral, cubical, triangular, different type of voids. Shape will be there. Depends on, here you see what you are generating, student, triangular type of voids. Triangular, this is triangular in shape.
Yes, sir.
If you have two dimension, okay, this we understand now. So these are triangular in shapes. These are triangular in shapes here. ठीक है? Triangular in shape.
Yes, sir.
So four spheres, and also if the centers we join, this was what type of shape? You can see this is a different shape. And these are triangular. The voids, empty spaces. What is the shape? Triangular. Triangular, student. ठीक है? These are triangular in
Yes,
shape.
sir.
The triangular voids are of two different types. In one row, the apex are pointing upwards, and in the next layer downward. What is this? This triangle you see like this. The other triangle is like this. In one,
Yes,
you
sir.
can see these triangular voids are of different shapes, student. ठीक है? The
Yes, sir.
the triangular voids are of two types. Two types of, pay attention to everything, because in three-dimensional everything will be used. As I said, this chapter involves imagination and visualization. So visualization and imagination is involved, because it is difficult to draw the exact pictures. Only we have to take it from some material of NCRT or somewhere. Some sources we have to take the picture student. I will not be able to draw in exact dimensions. It is not possible. So just to explain to you, we have to pay attention and visualize, student, visualize, because three dimension will be more visualization will be involved, more imagination. This is a imaginating, a lot of imagination will be here. So you will see that how much your brain can work. Your brain is like a parachute, and if you don't open the parachute, it will remain closed. It will not work. When the parachute works, when it is opened. You have seen divers diving from a height, big height,
Yes, sir.
from a
Yes, sir.
very high tower, and the parachute opens, then they land safely. If the parachute doesn't open, what will happen? Nothing. They will die. You have seen those people diving from aeroplane height of 20,000 feet. Your mind is, a lot of students' mind is closed. Their parachute is closed. So what will they learn? Nothing. So you have to open the parachute of your mind. That means that's why I ask so many questions to students. Say, I'm not hurrying up anything. I'm paying attention. See, I can miss it. Yeah, this is the packing. But see, everything is important. So triangular wires can be seen, but this apex is on top. This apex is on the lower side. You can see the difference. So two types of triangular wires in two dimensions. Okay? There are two types of triangular wires. Students.
Yes, sir.
Okay. So we understand two dimensions, students. Actually, you can see that what is happening. If you have this type of thing, students, you see that if I join the center of these student, and you can see inside this is a void. Inside this is a void. Why they are called triangular voids? Not because this is exact triangle in shape, but because you can see if I join the center of these constituent atoms or spheres, that is a triangle. That is a triangle. You can see that triangle. Okay. So this is a two-dimensional story. Now we will go to three-dimension student. What we are talking? Closed packing. Closed packing. The particles are packed closely. Okay? Now I am saying closed packing in three dimensions, students. Three dimension. How first you will have two-dimensional packing, then you will start the third three-dimensional packing. Yes or no?
Yes, sir.
How many types of two-dimensional packing I have told you? Tell me, how many types of
Two
two?
types.
Huh? One is cubical. Okay? Close packing in three-dimensional. All the real structures are three-dimensional. You know that. All the real structures are three-dimensional structures. So they can be obtained by stacking two-dimensional layers one above the other. Okay? So, but close
Yes,
packing
sir.
in two dimensions are two types. So what we can do, student?
Square close packing and hexagonal. Yes, sir.
So we are now going to three-dimensional. Everything is three-dimensional. Reality is three dimensions. What do you see, experience any crystal or anything? So how will you obtain them? There are two possibilities. First one is we are saying three-dimensional close packing from two-dimensional square closed packing, student. What we mean by that? What we are saying, students, that you in the two-dimensional close packing, what you had, students? All layers same? Tell me.
Yes, sir.
Same, exactly same, students. Exactly same. ठीक है?
Yes, sir.
A, all layers A. ठीक है?
Okay.
All
Okay.
layers same. A. This is my scale. What is this? Scale two dimension. Till now.
Yes, sir.
Now what I will do? I have to make it three-dimensional, and I again put the same layers, exactly same layer one above the other, and keep on making
Okay.
three. So you put on the top of this another A layer, put on the top of this another A layer, another. So student, what type of pattern is there? Now you have first layer, second layer, third layer, all A, all A. ठीक है? Keep on repeating.
Yes, sir.
And this is what will give you student what we call as a simple cubic lattice. Lattice is formed when you have the particles, students, in three dimension. In three dimension. So three-dimensional arrangement of particles is what we call as a lattice. So this type of lattice will be what, student? Cubic, simple cubic lattice. Simple cubic lattice, student. And simple cubic
Okay.
lattice is what? All the layers are AA type. Same, and is obtained from square
Square close packing in two
closed
dimensions.
packed two-dimensional structure which we have shown you. And here is a arrangement of that, student. Here is a arrangement of that which is there. So when all the layers have the same arrangement, this lattice has a pattern. So this is the unit cell. This is also called the primitive cubic unit cell. What is this? Primitive.
Primitive cubic unit cell.
We have already shown you primitive cubic unit cell, student. You have seen,
Yes, sir.
we said we will have to keep on drawing these, students. Okay. And you said we showed it like this.
Yes, sir. Only on the corners.
Although they are all touching each other, as I told you, they are point particles. This is the story here. This is a pattern. Simple cubic unit cell will be obtained, student, when we have square closed two-dimensional packing, and we repeat the layers A type pattern. And this is the arrangement in simple cubic, student, in simple cubic. ठीक है?
Yes, sir.
Okay. So students, you have seen, all right. Okay. First one which we have shown you is this. Now the next three-dimensional, we have to move to the next three-dimensional packing. Let us see the next one. Now if we try to create, student, three-dimensional close packing from two-dimensional hexagonal packed layers. You have seen the hexagonal closed packed structures, two-dimensional hexagonal. ठीक है, where the coordination number was 6 in two-dimensional hexagonal closed packed, student. Now there are two ways what we can do. There are two ways what we can do. Interesting thing is this, students, that as you have put those layers, student, we have shown you there are voids, there are empty spaces. There are empty spaces, students. There are empty spaces. So students, if I place the second layer over the first, see, there are two ways of doing it. How will I do it? Third layer I have to put, students. What I am saying, students, when placing the second square closed, we have already done that. If in the three-dimensional, students, can be generated by placing one layer over the other. So I will put another layer, placing the second layer over the first layer. So if I take hexagonal close packing such that the spheres of the second, okay, are placed in the depressions of the first. If I, there were depressions in the first layer. If I put the spheres, student, in the depressions, of the first layer, depressions of the first layer. ठीक है?
Okay.
Depressions of the first layer. The spheres of now the spheres of two layers are aligned differently. Spheres of two layers are aligned, student, differently. How? Differently. So if first is a layer, this is a different layer. This becomes B layer. How the B layer is obtained, student? See this, on the bottom of this you have a student, on the bottom of this you had the hexagonal closed packing. ठीक है? And on the depressions you are going to put, student, on the depressions of that you are going to put those second layer. ठीक है? So what will happen, student? The spheres of two layers are aligned differently. So what you will find that not all the triangular voids of first layer are covered by the spheres of the second layer. You will find, student, if you can do this by using some coins. If you take any coins of 20 or 30 coins of the same size, you can form a layer, first layer, and you will see there are depressions in the coins. Then on the depressions, you start putting the second layer. ठीक है? On the depressions of the first layer. So when you will put that, what you will find, student? This will be my second layer. You will find that when the second layer is put on the first, not all depressions, not all depressions will be covered, student, will be covered by the spheres. Not all depressions will be covered by the sphere. This is important point because, as I said, this imagination and visualization is started now. So not all the triangular voids of the first layer are covered. Not all the depressions. What are depression? Triangular voids. Not all the triangular voids, students, will be covered by the spheres of second layer, which I am putting B layer. This is my A layer. On that I am putting the second layer, which is the B layer. Okay? So this gives a different arrangement. So whenever a sphere of second layer is above the void of the first, whenever a sphere of second layer, whenever a sphere of second layer is above the void of first layer, what will happen? A new type of void will be generated. Okay? But a new type of void will be generated, student. What is that? A tetrahedral void will be generated. Tetrahedral void will be generated, student. What I am trying to say? देखो, here, student, learn me. This is not a very good drawing. That is the problem in this. We have to be very good in drawing, student. This was my, this is a void triangle. ठीक है? This is a triangular void.
Yes, sir.
Now on this void, you
Yes, sir.
have the second layer. What we said, the second layer should be on the voids of this. ठीक है? Second layer should be on the void of this, student. What it means? This is the second atom. You can see that. Now you can see that there is a empty space between the vacant. There is a void in that. This is a void. This one.
Okay.
This is generated by, this is a triangle on the lower triangular void, and on the top of that you are putting another sphere. This is a tetrahedral void. This is a tetrahedral void, student. This is generated when I am putting the B layer on the depressions of the first layer. ठीक है? ठीक है?
Okay.
Whenever a sphere of second layer above the void of the first layer, a tetrahedral void will be formed. ठीक है? So the tetrahedral void is formed when the spheres of four spheres are joined. Why did I say tetrahedral? The void is not tetrahedral in shape, but because students, what is a tetrahedral? If I join these four, if the I join the centers of these four spheres, student, then what happens? देखो, if you know what is a tetrahedral, you are aware of this. See, this is a triangle, student. You can see, and on the top of this is another one. What if I join this inside that? What will it be? Tetrahedral. You have seen the tetrahedral shape, student. ठीक है? The drawing may not be that good, so I don't want to confuse you. But here it is more visible in this. If you take three dimension on the top of these three, they are forming triangle, and if you join them, the centers of these, what will be there? It will be tetrahedral in shape, right?
Yes, sir.
Okay. So this is a formation of a tetrahedral void. And student, as I said, if you will use your coins, not all the not all the voids will be covered by the layer B. Certain voids will be left, student. So at other places, the triangular voids in the second layer are above the triangular voids of the first. What is more interesting? Two types of voids are being produced. First type of voids, student, we are saying are those when you are putting the second layer sphere, okay, on the void of the first, but certain voids are left when you will put this, and the result of that will be that will be at other places triangular voids in the second layer are above the triangular voids of the first. What we are trying to say, important point, we are going to say it here. First you are saying, first what I said, student, when you are putting layer second layer sphere on the second layer sphere is put, student, on the triangular void, on the triangular void of first layer. What you are getting? Tetrahedral void. ठीक है? Here we have shown this is my tetrahedral void. You can see this is the first layer. This is a triangular void. On the top of this, you are putting this atom. But when you will put the second layer B, student, second layer is my B, first layer is my A. ठीक है? A on B is the second layer, A is the first layer. Tetrahedral voids, and there are certain voids which will not be covered. ठीक है? Which will not be covered. Then what is the result of that? At other places, you can use your own coins and try to build it. You will be able to see that. At other places, triangular voids of, ठीक है, triangular voids of second layer, which is the second layer? B. Second layer are above the triangular voids of students, triangular voids of the first layer. Which is the first layer? A layer. ठीक है? So how many? There are two triangles opposite to each other. Then how many spheres are there? One of them has the apex of triangle pointing upward, other downwards. One of them has apex of the triangle pointing upward, and other has apex of triangle pointing downward. Student. And this will be a different type of void, student. These voids are called octahedral voids. So there are two type of voids which are generated, student, and this is what is your tetrahedral. Tetrahedral. You see these three, the atom is coming where? The second layer atom is coming on the top of this. Okay? This is the second layer atom where it is coming, this one. This is the tetrahedral. In octahedral, what is happening? The first layer, this is the triangular void, student. On the top also is what is another triangular void. There are two triangles. Each triangle has a void, yes or no? Each triangle has a void.
Yes, sir.
And they are placed in such a way that the apex of one is upward and the apex of the other is downward. The apex are opposite to each other. So if I will put one over the other, this will be a whole, student, which will be bigger than the tetrahedral hole. This is a tetrahedral hole, this is octahedral hole. Octahedral hole will be bigger than the tetrahedral hole, students. Octahedral hole or a void, student, is bigger in size than tetrahedral, student, void. And therefore, students, we have to visualize, we have to imagine now. Certain models are available somewhere, but I don't see any point of going into those details. They are not required for our exam. The questions, if we are able to solve questions, you have to consider it, try to see it. If you can't see it, then you remember it. There are two approaches to that.
Okay.
We don't want to go and waste so much time on the details, which is not in our course. Those students who are going to study crystallography, then they will be able to see everything. So how many types of voids we have generated, student? Two, tetrahedral and octahedral. Tetrahedral is generated by four. Join them, they will be the apices of a tetrahedron. Octahedral by six. Octahedral by six particles, as you can see, six spheres. And if you join, it will be a shape of octahedral, student. It will look like an octahedral. You already know the shape of tetrahedron and octahedral. We already shown that to you in geometry. You have seen, students. And when in closed pack, student, closed pack spheres, when they calculated the number of tetrahedral and octahedral voids in closed pack structures, students, the again we're not going to prove it here mathematically. It can be proved mathematically, but there's no point. In closed pack structure, student, in this you must know, closed packed, in closed packed sphere, students, if n is the number of spheres, or n is the number of closed packed sphere, if n is the number of closed packed spheres, then, students, the number of tetrahedral voids is 2 times of that. The number of tetrahedral voids is 2n, and the number of octahedral voids is, students, n. So this you should,
And
this is important point. What I am saying, let the number of closed packed sphere be n. After doing calculation mathematically, they determined all this. So we will say that if let the number of closed packed sphere be n, number of octahedral voids will be same as this, and total number of tetrahedral void will be 2 times of this, 2 times of this in the closed packed structures. In the closed packed structure, students. So when closed packed structures will be formed, students, like FCC. In FCC is a closed packed structure, which is same as CCP. This is also called cubical closed packing, or HCP. These are closed packed structures.
okay.
And number of atoms per unit cell is how much? 4 per unit cell. How much? 4.
Four.
So there are 4 atoms per unit cell. Therefore, the number of tetrahedral voids will be how many? Per unit cell, I'm saying number of tetra.
8.
Per unit cell
8.
will be how many? 4 into 2, 8.
8.
And number of octahedral
8.
bytes per unit cell
4.
will be same as this. Per unit cell student will be 4. Important point to note, because this will be very useful for solving the questions which will be doing student. Numericals will be asked student, and they will be important question. That will be important question student. So student, first layer we have placed, and we placed the second layer B on the voids, triangular voids of the first layer. But not all the voids were covered. Not all voids were covered. Okay? The voids which were covered were forming tetrahedral holes, and the voids which were not covered were forming the octahedral voids. So we have generated two types of voids now in the second layer. Okay? Clear? You
Yes,
got
sir.
it? Tell me.
Yes, sir.
You have student A layer, you have put the B layer. In the B layer, certain atoms, certain spheres occupied the were on the were on the triangular voids of the first layer. What they formed? Tetrahedral void. Certain voids, certain spheres
Okay.
were not on the tetrahedral voids. What they formed? Octahedral voids. How many type of voids you have?
Octahedral voids.
Two types of voids in the.
2. 2 types of them.
Okay, now we have to place the third layer student. What we have to do? We are going to place the third layer on the second layer now. There are again two possibilities. What is the two possibilities, students? What I am saying, you are going to place the third layer student over AB layer. Okay, these are two layers now. How many layers are these? Two layers. Okay, clear?
Yes, sir.
You have AB
Yes, sir.
student, AB layer. In this AB layer student, this is 1 plus 1, 2 layers. Okay? In the AB layer student, in the AB layer, you have tetrahedral voids and you have octahedral voids. Clear?
Yes, sir.
Two types of voids. Now, if you put the third layer, student, okay, covering the tetrahedral voids, ठीक है, tetrahedral voids of the second layer, covering the tetrahedral voids of second layer, ठीक है. The spheres, you will find that the spheres of the third layer are exactly aligned, are exactly are exactly are exactly student aligned. Pay attention, not fast, slowly. Are exactly aligned student, aligned, ठीक है, to the first layer, are aligned to the first layer. Which is the first layer? My A layer. ठीक है, ठीक है. So you are getting A B A, ठीक है.
Yes, sir.
You are getting ABA, and then again you find that the next layer will be B, and then again A B A B A B, like this. So students, the third layer in each case is the same as the first layer. ठीक है, this is the third layer, this is same as
Yes, sir.
this is the fifth layer, is same as the third layer. seventh is same as the fifth layer. Like this the pattern repeats, students. ठीक है? So pattern of sphere is repeated in alternate layers. The pattern of spheres, pattern of sphere, student, is repeated in alternate layers. ठीक है? And this is structure is called hexagonal closed packed structure. This is called hexagonal closed packed structure,
Close pattern.
HCP. HCP, student. Here you can see this is shown, student, three-dimensional. First layer is A, second is the B layer, and the first layer is exactly aligned with the third layer is exactly aligned with the first layer. And then next layer will be aligned with the B layer, student. And like this it will continue. So what type of pattern you are
Okay.
getting? AB type of pattern. So this is called the hexagonal closed pattern. The tetrahedral voids have been used in the second layer. Which voids? Tetrahedral. Clear?
Tetrahedral wall.
Examples are the
Yes, sir.
magnesium and zinc. देखो magnesium and zinc metals, student, they show this HCP, hexagonal closed packed structures. ठीक है?
Yes, sir.
The second possibility is, student, covering the octahedral voids. So if the third layer is, student, third layer is placed, student, over the octahedral voids, over the octahedral voids of second layer, ठीक है? Second layer is B, student, octahedral voids of the second layer. Then you will be able to generate, student, a layer which is not aligned with the first one, not aligned with either first or second layer. And this we are calling as, this is a new layer, this is called C layer. ठीक है? C layer, a new layer is generated. So this pattern is ABC. And again it is repeated ABC type. ठीक है?
Yes, sir.
The fourth layer will be same as the first layer. Fourth layer will be same as
First
the
layer.
first layer. Fifth layer will be same as the second layer. Sixth layer will be same as the third layer.
Second layer.
This
Third
type
layer.
of arrangement is called, student, cubic closed packing or face centered close packing. ठीक है? What we call CCP and FCC. ठीक है? First one I told you, ABABAB means hexagonal closed packing. CCP, FCC means cubical closed packing. So this is the picture. A, B, C is not either same as B or A. But after C, you will get the A, then B, then C. Then this pattern will repeat. This is called cubic closed packing or FCC, students. And iron, copper and silver, they are examples of CCP structures, students. They are examples of CCP structure, cubic closed pack structures. ठीक है? Cubic closed pack structure.
Okay.
So
Okay,
there
sir.
are three dimensions CCP. To remember when I said ABC, C means CCP. C means CCP, cubic closed packing, because it is ending with ABC. One is ending with ABAB. That is HC, hexagonal closed packing. Now I'm saying ABC. So this end with C, I am saying CCP. CCP is same as FCC. Got it? This is a
Yes, sir.
way to remember it, student. Two types
Okay.
of packing. They will ask you what is the difference between CCP and SCP. In CCP, you have layer, B layer, C layer, then the fourth layer repeats. In the FCP, you have A layer, B layer, then the third layer is same as the first layer. And you have seen how it is formed, student, how it was formed. When you put the third layer over the tetrahedral void, you will get ABAB. And when you put the third layer over octahedral void, you will get the CCCP. And in both the cases, student, the coordination number is 12. Important point, such questions are asked. One can visualize the coordination number is students 12. Coordination number is 12 students. There are diagrams to show that how it is 12. The nearest neighbor will be 12 in such cases because how many atoms will touch any atom? 12. In both the cases, in HCP as well as in CCP. What is the coordination number? This is a point to be noted here.
12.
The question is going to be asked. Many 10 times this question has been given. So if you are not able to visualize, imagine, at least you remember this. In the three-dimensional CCP or FCP, what is the coordination number?
12.
Clear? Clear?
Yes, sir.
So students, we end up the closed stack structure here, and we will continue further more about this because this needs a lot of visualization, imagination. Okay, then good night. I will see you in my next class. Okay?
Okay, thank you, sir.
Okay.
Yes, sir.
All right.
Thank you, sir.
Okay.